那我们就开始今天的那个 curvature part。那今天我们很高兴邀请到那个印第安纳大学的郭孝煌教授。那郭孝煌教授之前大学是这边毕业的，2007年毕业，然后之后去台大念硕士，然后后来到美国的 Rogers University 念 PhD。那他的那个 research interest 是geometric analysis 跟 differential geometry and partial differential equation。那今天他给我们带来的 talk 是 mean curvature flow and self-linear solution。那我们欢迎郭孝教授。
谢谢魏老师介绍，好，谢谢大家参加这个演讲。So today I'm going to talk about mean curvature flow and self-linear solution. So let me first introduce what mean curvature flow and also the entropy. So by mean curvature flow we mean it's a motion of hypersurface which velocity is given by the mean curvature vector. So here you can see a picture which illustrates the situation. So imagine you have a deformation of hypersurface and the velocity which is the velocity is given by the mean curvature vector. So that's what I mean by the mean curvature flow. And by mean curvature vector it is defined to be the sum of the principal curvature and times the uninormal vector. And because the mean curvature vector can be written as the Laplacian of the precision vector, where x, we use capital X means the precision vector. So sometimes you can see this equation looks very like the heat equation. So there's the mean curvature flow.
So how do you choose the direction of the normal vector?
You can choose, so it doesn't matter because once you fix one direction, so for example you can choose the outward normal vector as your direction, and then the mean curvature will choose the sign accordingly. So the mean curvature is determined by the choice of your uninormal vector.
就是说你的意思说 h 跟 n， 要不然是这个若变号，那个就跟着变号，对不对？但是我的意思就是说，其实我觉得他问的问题其实挺不错的，因为有些 flow 的话，其实你是必须要先把 normal 给确定出来，因为 mean curvature 的特性是这样，但是有一些 flow 就是说它的 speed 并不是 mean curvature， 那就会 depend on， 就是说它还是表达这个 flow， 但是它会 depend on 你的 choice of normal， 你知道意思吗？
Let me answer.
我讲中文可以吗？
可以，没问题。是这样，因为mean curvature是这样算的。首先呢，它是，对。首先，一旦你去决定这个 uninormal vector， 不管是你往外还是往内，一旦你决定以后，那我们是根据这样的方法去算出你的 mean curvature。所以看你怎么决定你的 uninormal vector。如果你决定什么，那你的 mean curvature会根据它的情况做变化，所以那不是太大问题。那重点是 h 乘上 n 呢，这个东西永远跟你怎么决定这个 uninormal vector 是无关的。More generally, you don't have to choose the mean curvature vector to be the velocity vector. So here we can consider more general curvature flow. So now let me use capital S to be the symmetric function of principal curvatures. So we can also consider a motion of hypersurface which velocity is given by what we call the S curvature. So for example, if you take S to be the sum of the principal curvature, and this is exactly the mean curvature flow. And also some people will consider this kind of flow. If you take S to be the inverse of the mean curvature, then this is called the inverse mean curvature flow. So we have lots of curvature flows.
But if x is an even function, then it does depend on the direction.
Sorry, say again.
If x is an even function.
Even function.
Yeah, then it does depend on the direction.
What do you mean by the even function?
Like x squared.
Oh, yeah, right. So here we want the function to be symmetric in the variable. So for example, you can consider a couple of ones with maybe in this way. Yeah, in this case, maybe it doesn't depend on the choice of a unit.
It does not, does not. You said it does not.
Does not. So now let me see. Let's see the existence and unique theory for this kind of curvature flow. So given a hypersurface sigma, and it's assuming smooth property values and curves, which means it's compact without boundary. And suppose now this given function, this given symmetric function S is defined on sigma, which means that this kind of formulation. So for example, if you come back to this example, the inverse mean curvature. In order to make sense of this inverse mean curvature, you have to, for example, the initial hypersurface has to be mean convex in order to make sense of this definition. So whenever this is defined on the initial hypersurface, and with one more condition, if all the partial derivative of S function is positive on the initial hypersurface, and sometimes this is referred to as the parabolic condition in terms of the PD. So once with this condition, then we can guarantee there will be some positive number T and a unique S curvature flow, which is defined from 0 up to the time capital T, such that the initial hypersurface is exactly the given hypersurface. So this is the existence and unique theory for the general S curvature flow. And notice that if you choose S to be the sum of the principal curvature, which means that if the S curvature is equal to the mean curvature, then such condition will hold very trivial, because if you take the partial derivative, this is equal to 1. So in this case, the conclusion is that the mean curvature flow is actually well defined for any given initial closed hypersurface. And not just about that, there's some special property for mean curvature flow. If you remember the first derivation formula for the area, so let me be more precise. So let sigma T be a deformation of hypersurface. Then the rate of change for the area is given by this equation. It's the integral of the negative mean curvature and the inner product with the velocity vector. So now, if you compare it to the mean curvature flow, then the velocity vector will be given by the mean curvature vector. So in which case, this integral will just become the integral of negative square of mean curvature. So it means that this quantity is always less than or equal to 0. So it means that the area is not increasing along the mean curvature flow. At least if you start with the closed hypersurface. So there is some property for the mean curvature flow. And because of this reason, so the mean curvature flow curve in R2 is also called a curve shortening flow. And there's a separated theory for curve shortening flow, which is given by Gage, Hamilton, and Grayson. So now, given any simple closed curve in R2, so if we consider the corresponding curve shortening flow, and this flow will make the curve become more and more round until it shrinks to a point in finite time. And actually, this kind of theory also holds for higher dimension, but with more restricted conditions. So in higher dimension, in the case of higher dimension, this is what's proved by Husken. So if the initial hypersurface is convex, then we have the similar conclusion. The mean curvature flow will make the convex closed hypersurface become more and more round until it shrinks to points. But what's special for the one-dimensional case is that the convexity condition does not require, and this actually is due to Grayson's theory.
所以说，通常你的mean curvature flow的证明呢，因为有些人会有一个错误的，我是认为是错误的 understanding， 就是说这个高纬度如果证明出来的话，自动就 imply 低纬度的就出来了，因为他们是做 dimension 是 n 的，那有些是因为 n 嘛，对不对 ？n 大于等于1嘛，对不对？那所以说高纬度如果是对的话，那就 imply n 是等于1是不对。其实这应该是不对的。你知道为什么？
就我所知
不对嘛，因为你刚刚那个一维跟高维的结论就是不对，因为你在高维的时候你会有 neck pinching， 你知道是吗？就是 engine 呢，它是 embedded 的，但是它一半到一半的时候它就断开来了嘛，你知道是吗？那就是有人就问我这个问题，我有些时候不大容易回答这个问题，就是说 你知道为什么吗？
至少我可以就你这个 net pinch 的事情来。
因为我是这么认为的，就是高维度的时候，他们总是 estimate 这个 second fundamental form， 但是 second fundamental 它一维的时候，它是没有，你知道对吗？所以那些估计的话，你 reduce 到一维的话，其实就变成有些等式的话，它 n 等于带进去的话，就知道0是等于0，或者0是大于等于0。所以你一维的时候，你没有得到任何这个 useful information。所以为什么你要在一维的时候，你是要额外去做？
对，的确，至少已经科学 flow 的时候，一维跟
因为高维不一样嘛，
对，是不太一样的。对，一维的东西很多情况是没办法碰到高维。但反之也一样。Okay. Right, so let's come back to so we know that the area, at least for the closed hypersurface, is not increasing along the curvature flow. But for unbounded hypersurface, the area is infinite. So these kind of things does not become not so useful. So we want to find some other quantity which is also not increasing along the mean curvature flow. So because of this reason, let's consider following what we call the Gaussian area of the hypersurface. So given the hypersurface sigma, and now let's fix the point P and also T positive, we define the Gaussian area of sigma to be this this integral. So basically what this integral says is that it's the integral of the Gauss function over the given hypersurface sigma. And P is sometimes referred to the center of the Gauss integral. And T is somehow related to what we call a scale. And here we have a proposition. So suppose the given hypersurface has the following condition. So what it means is that the area ratio is uniformly bounded, no matter how you choose to go both. So suppose this kind of condition holds, then it's not hard to prove that actually the Gaussian area will be finite. And not just finite, actually it's uniformly bounded, which is is bounded by a constant independent of the choice of P. So the bounded area ratio will imply this kind of things will be uniformly bounded. So now here comes the definition. We define the entropy of hypersurface. Actually, this is the idea notion introduced by Coding and Nicosh to be the supremum of all the possible Gaussian areas of sigma. So this is some property for the entropy. The first property is that the entropy of a hypersurface actually is invariant under translation and scaling. That means that the entropy of alpha times sigma minus p, if you do a translation by p vector, and then followed by doing some dilation by alpha vector. And actually it doesn't change the entropy at all. So for example, if you have two spheres, they have a different radius, actually they will have the same entropy. And secondly, the entropy of any hypersurface is always bounded from below by 1. So what does 1 mean? It means the entropy of the hyperplane. So hyperplane will have the minimum entropy among all hypersurfaces. And now let's see some other example given by Stone. So he computed the entropy for the cylinder and also sphere. So for example, for the cylinder S1 cross R of n minus 1 is about 1.52. And the next cylinder is about 1.47. And the entropy for the sphere is about the square root of 2. So this just gives some idea about what the entropy of certain hypersurface looks like. So let's come back to our point, because our goal is to find a quantity which is not increasing along the mean curvature flow. And actually, here we have. So by this theory, so by Fuskin's monotonicity theory, so we will have the following results. If sigma t is the mean curvature flow, then the entropy is not increasing along the mean curvature flow. So in other words, entropy can be used as a Lyapunov function for the mean curvature flow, especially when your surface is unbounded. And now I want to show you this proposition. And actually you can regard this as some application of the previous theory. So let's come back to the curve in R2. Given a curve in given a simple closed curve in R2, let's call it with sigma, then we have the following results. We have following property. So the entropy of this simple closed curve is always bounded from below by the entropy of the circle. So in other words, the circle has the minimum entropy among all simple closed curves. So we know the straight line has a minimum entropy among every curve. But when it comes to simple closed curve, the minimizer of entropy will be given by the circle. I want to show you the idea of the proof, because in the proof you can also see some interesting application of the mean curvature proof. So once you are given a simple closed curve, let sigma t to be the corresponding curve shortening flow. So by Gauge-Hamilton-Grayson theorem, we know the curve shortening flow will make this curve become more and more round until it shrinks to a point. But now we don't want it shrink to a point. Instead, let's try to rescale this evolving curve in order to normalize the length. So let's call the corresponding rescale curve to be sigma hat t. So sigma hat t is just given by the rescaling of the original curve in order to make the length equal to, say, the length of the unit circle. So by using that, in this way we can actually by Grayson theory, this rescale curve will not converge to a point. Instead, it will converge to the circle because we rescale the length, and it becomes more and more round. So it just converges to a circle. And now we can compare to talking about the entropy. So here we want to use what we call the lower semi-continuity of the entropy. So which means that the entropy of the limiting circle, which is the limiting circle, will be bounded from above by the limit inf of the entropy of the rescale curve. And because we know the entropy is independent of the scale, so the entropy of the rescale curve is actually equal to the entropy of original curve, because the entropy is invariant under rescaling. And lastly, what we use here to get this inequality is that the entropy is a Lyapunov function for mean curvature flow, which means that the entropy of each time slice will be bounded from above by the entropy of the initial time slice. And this completes the proof. So this is what we want. So that's how we show the entropy, the minimum entropy among all simple closed curves is obtained by the unit circle. Actually, this kind of theory also holds for higher dimension. But the proof is much more involved. And in a low dimension, because we have this Gauge-Hamilton-Grayson theory, but in higher dimension, we don't have such theory. But this kind of thing still holds. The minimum, so for example, if we consider the surface, embedded curved surface, then the entropy of all this, the minimum entropy among all embedded curved surface will be the speed. And the proof is given by Ruan, Jacob Bernstein, and Jonathan Zhu. Next, I would like to talk about the self-similar solution for mean curvature flow. So before we come to the definition, let me first talk about this proposition. If you're given a mean curvature flow sigma t, then we can always do some rescaling of the flow by this way. So we call this be sigma alpha t, which is defined to be alpha times sigma, and also we do some corresponding change in the time variable. So what the sigma alpha t looks like is we just do some rescaling of the flow in the space-time. If alpha is bigger than 1, this is corresponding to the dilation of the original flow. And the way why we do this kind of rescaling is that the resulting flow is actually another mean curvature flow. So that's why we consider this kind of rescaling. And we call this kind of rescaling to be the parabolic rescaling of the original flow. And now here comes the definition for what it means to be self-similar. So when we say mean curvature flow, sigma t, where t belongs to I is the interval, where we take I to be either from negative infinity to 0 or 0 to infinity. The reason why we take this interval is because once we do the rescaling, the corresponding time interval will change. Once we take I to be these two choice of interval, then is independent of is invariant under after rescaling. Anyway, so when we say a mean curvature flow is self-similar, if it is invariant under parabolic rescaling, it means that if we do parabolic rescaling, it doesn't change the flow. So that's what we mean by self-similar. And according to I is equal to the first one or the second one, we have two types of self-similar solution. For example, if I is from negative infinity to 0, actually, if sigma t is self-similar, then each time size is given by just certain factor, which is square root of negative t times sigma negative 1. In other words, every time size they are similar to each other, but just differ by a factor. If I is equal to this choice, then the factor is given by the square root of negative t. And if I is equal to 0 to infinity, then this factor will be the square root of t. So that's what the self-similar solution looks like. And actually, because of this fact, we have the following observation. Let's first consider the first case. If I is equal to negative infinity to 0, then in this case, we know sigma t is equal to the square root of negative t times sigma negative 1. And now let's let t vary from negative infinity to 0. As t increase, you can see this factor will become smaller and smaller. So this corresponding to the fact that this flow is kind of shrinking itself. On the other hand, if in the second case, when I is from 0 to infinity, then when t increase, this factor becomes larger and larger. So in this case, the flow will expand itself. So we call the first flow to be a self-shrinking flow, while the second to be a self-expanding flow. So these are the two types of the self-similar solution. So let's first say something about a self-shrinking flow, mean curvature flow. So actually, if a mean curvature flow is self-shrinking, by that we mean it takes the following form: nt each time size is equal to a square root of negative t times a certain hypersurface. Then we call gamma to be the generator of the self-shrinking flow. If this is a self-shrinking mean curvature flow, if and only if the generator must satisfy this equation, which is the mean curvature factor plus 1/2 over x per equal to 0, where x again is a precision factor. By per we mean it's a projection to a normal space. And we call such a hypersurface to be a shrinker. So in other words, shrinker will generate a self-shrinking mean curvature flow. On the other hand, we have self-expanding flow. And suppose this self-expanding flow is generated by the hypersurface gamma, then the corresponding equation satisfied by the generator is the following. Is mean curvature minus 1/2 over x per equal to 0. So we call such a hypersurface to be expanded. So in terms of equation, shrinker and expander, they look very similar. They just differ by the sign in the middle. But actually later we will see they are quite different. So before we continue to that part, so let me first ask the following question. So given a shrinker, then we know it will generate a self-shrinking flow, which is given by nt equal to square root of negative t times gamma. So now, as t approaches 0, what does the limit look like? In other words, if you keep shrinking a hypersurface, what do you expect at the end? Let's first see some example. So let's first take, for example, if we take gamma to be a sphere, actually sphere is a shrinker because the corresponding mean curvature flow is self-shrinking. So now if you have a self-shrinking sphere, so as t approaches 0, you can see it just shrinks to a point. On the other hand, if we take the shrinker to be the cylinder, and by the way, cylinder is also a shrinker because the corresponding flow is self-shrinking. So at t approaches 0, this shrinking cylinder will shrink to a line. So now let me talk about, so what is the limit when you just keep shrinking a hypersurface? So we call this a limit to be the flow down limit. It depends on the choice of gamma. if gamma is bounded, then at the end, everything will shrink to a point, just like the first case. And however, if gamma is unbounded, for example, if you have cylinder, and the limit will be a cone. So what do we mean by cone? So let me make a formal definition for cone. So when we say a set C is a cone, if it is just a set which is invariant under rescaling, so it satisfies this kind of condition. So for example, if you have a line, then we also call this to be a cone. But we are interested in more regular cone, so let me also make the following definition. So when we say a cone is regular, it means that away from the origin is just a smooth hypersurface. And later we will basically focus on this case. So we will focus on the regular cone. And let me introduce this definition. So when we say, given a hypersurface gamma, when we say this hypersurface is asymptotic to a regular cone at infinity, if the flow down limits, that means if you keep shrinking this given hypersurface, eventually you will get a regular cone. So basically we will consider this kind of hypersurface. And we call this hypersurface to be asymptotic to a regular cone at infinity. The name comes from if you see this hypersurface in the distance, then it just looks like a cone because it keeps room out the hypersurface. And now let's come back to the shrinker. So we know if shrinker is, suppose given a shrinker, suppose this shrinker is asymptotic to a regular cone at infinity, that means that if you keep shrinking the shrinker, eventually you get a regular cone. So this corresponding to the following facts. Because we know the corresponding mean curvature flow generated by the shrinker is just shrinking itself. So this together with this condition, it means that this shrinking mean curvature flow will just converge to the cone as t approaches 0. On the other hand, let's consider the case of expander. If given an expander, suppose this expander is asymptotic to a regular cone at infinity, and now let's see what does that mean for the corresponding mean curvature flow generated by the expander. Because the corresponding mean curvature flow is the expanding of the gamma. So now if we go backward in time, as t approaches 0, this, because it's expanding, but if we go backward in time, it becomes shrinking itself. So as t approaches 0, this means that the mean curvature flow will converge to a cone at t equal to 0. But t equal to 0 is the initial time of the mean curvature flow. So it means that in the case of expander, this means the corresponding self-expanding flow comes out of the cone. So it means that n0 is the initial time, is the cone, and then n1 it arrives at a gamma, and in between nt is equal to the square of t times gamma. So here we have this kind of picture to illustrate the situation. So we start from the cone and then evolve to gamma. So this is what the expander, suppose the expander is asymptotic to the cone at infinity looks like. And now let me say something about the shrinker and expander. So we will have the following remarkable theory. So given two expanders, suppose these two expanders they are asymptotic to a cone at infinity. Suppose they are asymptotic to the same cone at infinity. Then they must be identical to each other. So in other words, so this is a rigidity theory for the shrinker, which is asymptotic to the cone. So in other words, given a regular cone, there's at most one shrinker which is asymptotic to this cone. On the other hand, such a theory does not hold for expander. And also this is proved by Jacob Bernstein and also Wang. So they show that they find a regular cone C in R3 with the following property. They can, so for this given cone, actually they can find at least three distinct expanders which is asymptotic to this given cone. So they are at least so in other words, the rigidity theory does not hold for the expander. So it's shrinker and expander, they are quite different in this sense. And now let me show some my result regarding these two theories. So in order to So first, let's come back to this rigidity theory for the shrinker. So I found that the rigidity theory does not only holds for shrinker of mean curvature flow, but also holds for shrinker for the more general curvature flow. So let me state my result. But before that, let's come back to this S function. So once again, given a symmetry function of the principal curvatures, and we can make an analogous definition for the S shrinker. So by that we mean if a gamma is called S shrinker, if it satisfies this equation. And in terms of the shrinker for mean curvature flow, this is just the mean curvature factor. And now we just replace that by the S curvature factor. So that's what I mean by S shrinker. So, and now we have the proposition. If this symmetric curvature function is also homogeneous of degree 1, which means that if S of alpha times X is equal to alpha times S of X for any positive constant alpha. So, for example, if S is a mean curvature function, it's a sum of the principal curvature, it has this property, it's homogeneous of degree 1. So now we will focus on this case. If this function is homogeneous of degree 1, then each S shrinker will also generate an S curvature flow, just like the case of mean curvature flow. So in other words, S shrinker is also the self-similar solution for the corresponding S curvature flow. And now let's state my results. So this is the rigidity theorem for the S shrinker, which is asymptotic to a cone at infinity. And now let's assume this curvature function is symmetric and homogeneous of degree 1. So the theorem is the following. So given a regular cone C, suppose that there exists some constant lambda between 0 and 1, such that the following condition holds on the link of the cone. So these conditions are, so firstly, all the partial derivative, not just partial, but also bounded between lambda and 1 over lambda. So this corresponding to some elliptic condition in terms of PD. And secondly, we want the second derivative of S, and also the difference quotient of the first partial derivative of S. They are relatively small compared to this elliptic constant. Suppose these three conditions holds on the link of the cone, then we have the conclusion. Then we also have the rigidity theory. There exists at most one S shrinker that is asymptotic to the cone at infinity. And notice that such condition, if you take S to be the mean curvature, which means that S is the sum of all the principal curvatures, then all these three conditions holds very trivially because, for example, the first partial derivative is equal to 1. And this one, the second derivative will be 0 because you differentiate 1, get 0, and this is also 0.
So this dI is dd kappa I or?
Right. Because S is a function of the principal curvature. So you just, you just differentiate with respect to the variable.
And Sn means?
Sn, which one?
Doesn't mean the sum of kappa I equal to 1.
So for example,
C is in the distance space.
So in the case of mean curvature flow, S is equal to kappa 1 to kappa n. So for example, D1S means yes by D kappa 1, which is 1. Just differentiate formally to the expression.
Are you asking the notation Sn or?
上面的 Sn 应该是 speed 嘛 ，C 跟 Sn 的交织嘛。
Oh, this Sn, sorry. So this means it's a cone. So a cone. So we want to see, because this function is homogeneous of degree 1, so we just want to see the intersection of the cone with the unit speed.
但是你说 symmetric function Sn 的话就是 kappa 1乘以 kappa n， 然后再开 n 分之一嘛，对不对
Right.
因为你要homogeneous degree 1嘛。
Right.
我问一下，你这些 condition 都是因为你在做 PD 估计的时候需要用到的，对不对？
对，
没有错吧？
对。
So I wonder So that is the sum of kappa height. Then all these is equal to 1.
Right. So the first condition, D1s or D2s, they are all equal to 1, so they hold. You can choose lambda to be 1 in this case.
So these derivatives, do you consider them as function of kappa height, or consider them as functions of Rn plus 1?
You first consider as just a function of this variable, kappa 1 to kappa n. And then we plug into this theory. When we plug this into this theory, we will regard this kappa 1 to kappa n to be the principal curvature of the hypersurface. But before that, we just regarded this as a function
of
n variable.
C. Of the hypersurface C.
Right. In this case, eventually we want to prime kappa 1 to kappa n to be the principal curvature of the cone C. So that's our first theory for about a rigidity theory for the more general curvature flow. And now let me come back to the second non-rigidity theory for the expander. So in general, expander does not have rigidity theory, but we still can say something under some extra conditions. So that's what we want to do next. In order to stay on theory, let me first introduce an idea which is called a normalized mean curvature flow. So we introduce another flow. So again, gamma s is called normalized mean curvature flow. It means that the velocity is equal to the mean curvature vector minus 1/2 of x curve. So you probably may recognize the right-hand side because when we talk about the expander, this is the corresponding equation. When this equal to 0, this is what we mean by the expander. So this actually comes from the second observation. So expander are the equilibrium or stationary solution of this flow. So we can regard this flow as the corresponding dynamical problem of this kind of equation. And let me also talk about this proposition. And in this proposition, it also explains what we call such a flow to be a normalized mean curvature flow. Because this flow comes from studying the asymptotic behavior of the mean curvature flow at time infinity. Later we will come to these parts. So this proposition says the following. If sigma t is a mean curvature flow which is defined for all t positive, if it only is gamma s, which is defined to be sigma t divided by the square of t, and also do some change of variable in time, we write t as e to the power s, then this will define a normalized mean curvature flow. So every mean curvature flow we will associate with a normalized mean curvature flow by doing these kind of things. So later we will come to this, will appear again when studying the asymptotic behavior of mean curvature flow. Now we can say our theory. So theory is the following. So now given the expander of mean curvature flow, and let's assume that this expander is asymptotic to a regular cone at infinity. So what we assume for this expander is the following. Suppose the entropy of the cone is sufficiently close to 1. Remember, 1 is the minimum entropy among all hypersurfaces. So now what we assume is that suppose this cone is sufficiently small in this sense, the small entropy condition. Then under this condition, we have the following conclusion. Now given any hypersurface gamma tilde, which is sufficiently close to gamma in the C2 topology, and also it is asymptotic to the cone at infinity. That means that for every nearby hypersurface of gamma, by nearby hypersurface, we mean two conditions have to hold. The first, this nearby hypersurface has to be close to gamma in the C2 topology. And secondly, this hypersurface is also asymptotic to the cone at infinity. So once these two conditions holds, then we have the following conclusion. Now we can evolve this nearby hypersurface by the normalized mean curvature flow equation. The normalized mean curvature flow equation will take this gamma tilde to convert to gamma as s approaching infinity. So let me draw a picture. So what I mean here is that suppose this is gamma, and this gamma is an expander which is asymptotic to the cone at infinity. And And now if you take a nearby hypersurface, it's called gamma tilde. Then suppose this gamma tilde is sufficiently close to gamma and asymptotic to the same cone at infinity. Then this, and now let's evolve this by the normalized mean curvature flow. Then eventually this gamma tilde will converge to gamma. So we have a correlate because of this theory. So the correlate is the following. So given if you have two expanders, they are asymptotic to the same cone, then they cannot be too close to each other. Because if they are too close to each other, then by our theory, then one will be taken to the other by the normalized mean curvature flow. However, the expander are equilibrium solution, so it cannot be moved by such a flow. So at least we can say something about the expander in this way. So they cannot be too close to each other. In other words, such an expander must be isolated. And lastly, let me talk about the connection with the asymptotic behavior of mean curvature flow. So let me first state this theorem. This is given by Husken. So somehow we use this theorem to characterize when does a flow become singular. So let sigma t be a mean curvature flow of closed hypersurface. Then if such a flow becomes singular at t approaches 0, it can only if the second fundamental form flows out approaching this time. In other words, the second fundamental form must flow out at the first singular time. Otherwise, the flow will never be singular. So by second fundamental form, we mean the norm of the second fundamental form is equivalent to the square the L2 norm of the principal curvature. So if this flows out, it means that at least there must be some principal curvature become extremely large. There's a natural question because we know the second fundamental form flows out at the first singular time. So how about the mean curvature? Does the mean curvature also flows out at the first singular time? So actually there is a conjecture. So people believe the mean curvature also flows out at the first singular time for lower dimensional mean curvature flow. But this may not be true for higher dimensional mean curvature flow. But there's no issue. But in the case of curve shortening flow, that means if you consider curve, then there's no problem in this case because in this case there's only one principal curvature. So the principal curvature is just equal to the mean curvature. So it must flow out by Husken's theory. But this question will become very non-trivial when you consider the surface. In this case, you have two principal curvatures. So the mean curvature is equal to the sum of these two principal curvatures. So there might be some cancellation. For example, one principal curvature is positive, the other is negative, and there might be some cancellation. So in general, this is a hard problem. But just recently, several years ago, this was proved by Li and Wang. They proved that at least for surface, the two-dimensional mean curvature flow is also true. The mean curvature also flows out at the first singular time if you start with a closed hypersurface. And I also have some results regarding this theory. This theory not just true for closed hypersurface, but also holds for mean curvature flow with what we call a free boundary condition. So if we consider the mean curvature flow with free boundary condition, and you consider a two-dimensional case, then such a theory also holds. In that case, the statement of theorem will be modified into a boundary setting. So at the first singular time, either the mean curvature flows out or the parameter. By parameter we mean the boundary, the length of the boundary curve will flow out. So this is another result, another result. But let's first come back to the singularity of the mean curvature flow. So we have some technical conditions. So if a mean curvature flow, when we say mean curvature flow develop a type 1 singularity at certain points at the origin, as t approaches 0, if the following two conditions holds. The first condition is that, so firstly we know As singularity, the second polynomial form must close out. So it just means that this is a singularity. But the second condition requires the rate of the blowout must be no more than this rate. If we have the control of the blowout rate, then we call this to be the type 1 singularity. Otherwise, it's called type 2. So Huisken has a following theorem. So if the mean curvature flow develops type 1 singularity, then the flow will be locally looks like just a self-shrinking near the singular points. So by that we mean if we rescale the hypersurface near the singular points, then this will convert to a shrinker.
我问一下，你知道为什么开放型号体要小于那个 c 根号比例？
因为这个东西它在做 rescaling 的时候，
它其实有一个很简单的，不是太难的。
对，它必须是这个 rate。对，
它必须是这样的。
这个 rate 太
基本上就是你的 PD blow up 跟那个 OD 的 blow up 看起来是一样，是基本上是一样，对不对？对。
一般来说 type 2的话，我们不知道它的 blow rate 是什么，所以
它这里是知道的。
当然还是有特殊的情况啊。Alright, so now so now this explains so you can see when studying the singularity of mean curvature flow, shrinker plays a very important role. So basically shrinker models the asymptotic behavior of mean curvature flow near singularity. And now let's see what the expander plays when studying the asymptotic behavior of mean curvature flow. So actually the expander will model the asymptotic behavior of mean curvature flow at the time infinity. So this is a theorem proved by Aker, Huisken, and Stavrou. So let's focus on the study of the mean curvature flow graph. That means now let's consider the graph of function. And suppose this graph, evolving graph, this is also a mean curvature flow. Now under the following two conditions. Suppose for the initial graph, the Lipschitz, this is a Lipschitz function. That means that the gradient is uniformly bounded by some constant. And also, the initial hypersurface is asymptotic to a radial cone at infinity. So under these two conditions, on the initial hypersurface, they can show that this flow will eventually become asymptotically self-expanding. That means the following. If we rescale the flow, then this flow will become more and more like an expander, gamma, where gamma is an expander which is also asymptotic to a cone at infinity. So expander will model the asymptotic behavior at time infinity. So I also have some result which is similar to this theorem. So we don't require to, so in my result, we don't require this to be a graph. Because in terms of graph, actually, we just reduce to study the corresponding PD of the function u. And let me show the result here. So instead, we don't have to assume the mean curvature flow is a graph. Instead, what we assume is the following. Suppose that the initial graph, so firstly, we still require this to be asymptotic to a radial cone at infinity. But instead of require this to be a graph, we assume that suppose the tangent cone has small entropy. The entropy is no more than 1 plus epsilon, where epsilon is some constant, depends on the dimension. Then we have the similar conclusion. The flow will become asymptotic self-expanding as T approaches infinity. So
那eventually会变成一个 graph。
不一定。Yeah, so that's what I want to talk about. 有没有什么问题的？
Does every regular cone have a shrinker?
Not really.
And do we know what kind of regular cone has a shrinker?
That's a good question. So I also have one paper on this kind of problem. So the result is that if we consider special case, they say if you take a rotational symmetric cone, then we can find a shrinker. And actually, you can find more general. You can find S shrinker. That means that the shrinker to the S curvature function. Suppose the function also has some other properties. So we just consider rotation in this case. At least in this case, we have the existence.
But is there a concrete example of cone where which is not a shrinker?
So, sorry?
Is there a concrete example of a cone which is not a shrinker?
Can you say again the question? The cone is.
Is there a concrete example of
right.
a cone which is not a shrinker of the
Cone is not a shrinker.
Yeah, but it doesn't appear the limiting set of a shrinker.
I don't quite understand the question.
Yeah, maybe I should say it in the shorthand. So is there a concrete example of a cone
Right.
which is not the limiting set of a shrinker?
Oh, you mean okay. So this is actually the same as the previous equation.
But I want to see a concrete example.
Concrete example. For this kind of concrete example, I have no idea. Probably we can find, but in general, yeah, I have no idea. But I believe there must be some such a cone, because it's impossible for every cone there must be a shrinker, which is a similarity to this given cone.
Why?
Because there's so many choices of the cone. So
Yeah,
it's
so
impossible,
many
no matter how you given a cone, there must be corresponding a shrinker, which is a similarity. But I cannot give a counter example. But I believe it should be.
我问一下，这些选口或是 expander 这些是不是都已经被分类了？
shrinker，首先 shrinker 的，它会着重在 shrinker 的分类，因为 expander 没有 rigidity。OK， 那 shrinker 的分类也很困难，因为还是太多了，所以只能再加更多的条件去分类。
加一些什么 convex 啊 compact 这些就比较清楚。
的确，而且 shrinker 的分类更重要，因为它可以研究 singularity。
To go back to the slide about the example of the entropy, then we gave a formula that is asymptotic to square root of 2.
Right.
Yeah, this one. And do you have any explanation why square root of 2 is here?
好问题这个是这样，它基本上我先说一下这个东西怎么算的。首先有一个 theorem 是这样，就如果你给的东西是给的首先 entropy 是这样定义的 ，entropy 是定义为所有的Gaussian area 的 supremum。但如果你的今天的 sigma 是一个所谓的 shrinker 的话，那它的Gaussian area 你不用找任何算那么多，其实它的 supremum 会 achieve 在 p， 你 choose p.0、p.1，所以换句话说就是最标准的那个Gaussian area。shrinker 的最标准的那个Gaussian area就是它的 entropy。那再回到这个例子来看，那这些东西它们都是 shrinker， 所以它们非常容易去算它们的Gaussian area， 所以是这样去算出来。所以你只要算它们相对应的Gaussian area， 你就知道这些数值怎么来。那至于这个东西，它就是算Gaussian area， 然后你就出来了。
刚刚说那个Gaussian area就是用那个kernel去做的，对不对？
对。
那假如说你的 flow 不是 mean curvature flow， 你的 entropy 就是要用不同的 kernel 去做的。
这是好问题，但是它 mean curvature flow 会这么多结果，是因为主要是这个所谓的monotonicity formula。
对嘛。
因为这个monotonicity formula才会让这个 entropy 它特别的重要。
所以考虑不同的 flow， 乱七八糟的 flow， 可能 entropy 就没有什么好的性质。
对，是因为我们想要monotonicity， 那这也是为什么它可以用这个 self-similar solution 会 model 这个 singularity 的关系。那一般 flow 就 就不一定有那么办法用这样去证明出来这样，就好像在研究这个 minimum cone 一样 ，minimum cone 在也是类似的情况，因为有麻烦的 set form 可以研究，那至于更一般的就可能比较困难。
各位还有没有什么其他问题？没有的话，我们再次谢谢郭小宝。